Okay, so we're going to start off talking about ultrasound today, and there's a lot. It's, ultrasound is a different modality. There's different modalities when we talk about imaging, and we just got through talking quite a bit about radiographs. That's one modality is X-rays or radiographs. Another modality that is commonly used is ultrasound, and other modalities would include things like CT and MRI and nuclear medicine studies and things like that. But now we're going to switch over. We're going to talk a little bit about ultrasound. We briefly mentioned before when we were talking about abdominal radiographs that ultrasound is similar in some ways, but it's different in some ways than radiographs, and they're complementary procedures. And so we want to keep that in mind, in that there's some things that you can see really well on radiographs, but you don't see well on ultrasounds. And then there's other things that you can see a whole lot better on ultrasound that you really can't see on radiographs. And so it's not one or the other, it's usually one and the other when we're talking about those two modalities as far as radiographing small animals. Unfortunately, we have to talk a little bit about physics. And the reason why you need to know this is we have to know a little bit about how the machines work, how the sound interacts with matter that come out of the machines and what that reacts inside the body. And we have to, that will help us understand the images that we're seeing, and will also help us understand some pretty classic ultrasound artifacts that we have to understand so we know if they will help us make a diagnosis or hinder us from making a diagnosis. And so this is the kind of the basics that we're going to start with is ultrasound physics and how does ultrasound machines work and how does it turn up and make an image that we can use diagnostically. So in general, if you really want to break it down into the basic, concept, is the ultrasound machine makes sound waves. Okay, the sound waves then go into the body. They bounce off of things, and a picture comes out. That's in general. That's but we have to get to know it a little bit more in depth than that. Ultrasound basically got its general start back in the early 1900s, so 100 years ago or so. And it got its start in marine stuff, so boats and ships and things like that. So a lot of people were starting to research it, and it got its start with what's called sonar, which is an acronym that stands for sound, navigation, and ranging. In about 1912, when the Titanic sunk out in the Atlantic, they tried to use this new thing called ultrasound and sonar to try to find the Titanic, but it seems like that most things with that voyage didn't work out too well, and so the ultrasound didn't work out too well to find the ship. So it was kind of unsuccessful at that time. Then again, in the 40s, during World War II, the Germans, believe it or not, which is pretty typical because they were really good engineers, they used it very successfully, mostly against the US and the Allies trying to find submarines in World War II. Medically, it started being useful in the human side of things in the 1950s. And everything in any type of equipment, electronic stuff that you want to think about, back then the ultrasound machines were huge. They were, the size of large beds, it seems like, and the probes were huge, and they put out a lot of heat, and things like that. And now, of course, the ultrasound machines, they have some that, can work on your Samsung iPad and some that work in the palm of your hand. So they've come a long way. If you look at the images from some of those early ultrasound machines, it's kind of like Bertha's X-ray. You can kind of see what's going on, but the image quality is obviously very poor. In veterinary medicine, probably in the mid to early 80s is when the vet schools started having ultrasound. And for the most part back then, they wouldn't buy the ultrasound. It was donated from some human hospital when they were upgrading their ultrasound machine, and they'd give their old ultrasound machine to the veterinary schools. And again, those ultrasound machines early on in the vet schools were piss poor. You go back and look at those images, and I don't know how they really got to see much of anything on those poor quality images. Now, I would bet that 50, maybe even 70% of veterinary clinics out in the US and probably Canada have ultrasound capability. They have an ultrasound machine in their office. I think the real question, though, is of those clinics that have ultrasound, how many of them really know how to do ultrasound? And I think that percentage is much lower. So of all the clinics that have ultrasound capability, I would bet if you don't count just being able to find bladder stones and fluid in the abdomen, I would bet only 30 or 40% of those clinics really know how to do ultrasound. And so that's where this is going to start. When you get out, you're young, you know, all you're going to get hired for the most part, most of you, by other veterinarians that are older, have, you know, they own the clinics and stuff like that. And they're going to just assume that because you just got out of vet school that you're going to know how to do ultrasound, which is obviously a false assumption, but you're going to know more about it than they probably do, hopefully from this course. So here's a little cartoon about sonar back in the day. And so you can see there's a ship on the top of the water, and the ship, on the bottom of the ship, somewhere in the hull, it had a ultrasound transducer. And when they wanted to, it would send out a wave or a volley of sound into the ocean, into the water underneath it. And that sound would propagate into the ocean as it got deeper and deeper and deeper. So it would send out these sound waves. And between the sound waves, there was no sound. So it would have a ping like ding, 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 like that. And you would see these sound waves coming out. They'd go into the ocean, the medium in which they would travel, and then they would bounce off of things. And so if it was a submarine or a fish, like fish finders that work the same way, or the bottom of the ocean or the bottom of the lake to tell how deep it is, then a portion of that sound would reflect off something and then would bounce off of it and then reflect back towards the bottom of the boat. And that transducer on the bottom of the boat then would pick up that sound, it would detect it, and convert it into some type of useful information. And of course, for us with medical imaging, that fancy machine, that computer inside that machine converts that sound into a anatomic picture of that organ. It's pretty amazing when you think about it. So we have to think about what are the physical properties of sound that we need to kind of concentrate on. Well, the first thing that you have to realize is that sound, as you learned from basic physics, sound is a wave form of energy. And so when I'm talking to you, you know, if you were in the room really, and when I'm talking to you, the sound comes out of my mouth and it comes as a wave form that propagates through the air molecules. And then, you know, that allows you to hear that sound. And because it has properties of a wave that we learned from physics, you can describe all waves with different, you know, properties. So it has a velocity, it has a frequency, it has a period of wavelength and amplitude, all that kind of stuff that we learned in physics. For ultrasound, though, we can kind of simplify that, and we can only have to worry about the sound waves with ultrasound only has a velocity and a frequency. Okay. Like all sound, it has to have a medium in which it travels. Again, the example, if you were here in my office and I'm talking to you, the medium in which that sound is going from my mouth to your ears is air. And we know that air is made up of nitrogen and oxygen, a little bit of helium, a little bit of other stuff too, right? If you were sitting in my office and there was a way that we could take out all of the air from the room and we would be sitting in a vacuum, right? So there's no air in the room, then I could be talking all day long and you wouldn't hear anything because now there's no medium in which the sound is traveling. On the other hand, when we're doing ultrasound medically, the medium is going to be water or soft tissues. Okay, we know that the great majority of all of our bodies is made up of water. And so we use that. That's the medium in which sound travels, is the water in the soft tissues, which is the majority of the soft tissues. The speed of ultrasound, and you can all demonstrate this too, you know, is dependent on the medium in which it's traveling. So if you go on one side of the Grand Canyon and you know you shoot a gun, it's going to take a few seconds for it to get to the other side of the canyon before you can hear it. And that's because sound in air propagates and travels relatively slowly. Okay. So the sound travel is dependent on the ultrasound medium in which it's traveling, the speed of the sound. And in air, it goes relatively slow. So anything that's not very dense at all, like air, the sound travels slowly. Okay. The more dense or stiff a substance is, the sound tends to travel faster. Okay. So if I'm standing on one side of the Grand Canyon and I have a steel pipe, let's say, and I hit that steel pipe with a hammer, it's going to take a few seconds for that sound through the air to propagate to the other side of the Grand Canyon before you would hear it. Okay. On the other hand, if I had a steel pipe and it was really long and spanned the entire length of the Grand Canyon, and you put your ear up to the edge of the steel pipe, you'd hear it really quick because the sound travels through the steel pipe a lot faster than it does in air because the steel pipe is stiff and very dense. Okay. So here's kind of a chart that goes to, it talks about the speed of sound in different mediums. And if you look here in air, it travels relatively slowly. So sound would travel about 330 meters per second in air. Okay. If I go down in here into things that are stiff, like metals and things like that, cortical bone and stuff like that, the sound travels much faster. So down in the 5,000 meters per second range. So there's a big difference in here. Okay. If you look in this range up in here, this is your soft tissue. Human or dog soft tissue is about 1,540 meters per second is the speed of sound that travels in most of our soft tissues. And it varies a little bit depending on how much fibrous tissue and how dense that tissue is. But for our purposes, what you need to know is sound travels in soft tissue 1,540 meters per second. And that's the number that all of the ultrasound machines use going forward to calculate the speed of sound and distances in the sound. Okay. The word ultrasound, the ultra part of that means the frequency is too high for us humans to hear. Okay. And if you remember, when you guys, you're young, and so you have great ears still. And when you're young like that, a human ear can hear up to maybe 22,000 cycles per second, or the frequency, which is the high pitched sound. So the really high pitched squeals and, high pitch instruments like piccolos and things like that. You can hear up to those frequencies when you have young, really good ears. As we all age, that top end of that ceiling will come down a little bit. And so when you get to be my age, you may not be able to hear those high frequencies as well as you did when you were younger. And you may only be able to hear up to maybe 18,000 hertz or something like that. Again, the ultra part of that word ultrasound goes along with the sound waves that come to the ultrasound machine are too high for us to hear. We are hearing in the low 20,000 hertz range. Well, ultrasound machines shoot out sound waves in the mega or millions of hertz range. So it's not only a little bit too high to hear, it's way too high for any human to hear, and even dogs and things like that, they can't hear it either. Okay, then we have to talked about the velocity of sound, and that it's dependent on the medium in which it travels. And now we have to talk about the frequency of the sound as it comes out of the ultrasound machine. And the easiest way to remember this, what I'm going to teach you here, is you look at an old-fashioned stereo speaker, and the speaker tends to have different components. So if you take off the grill of one of these old speakers and you look in here, there's a big round part in here that has a large diameter, and that's called the woofer in a speaker. And then you typically will have like a mid-range driver, and you have what's called a tweeter, and that's the high frequency. So that's the trebles and the cymbals and the piccolos and all that kind of stuff. And this is the bass. That's the thumping bass that would come out of that woofer right there. Okay. Now, the thing to remember is if we would turn the volume up, then this speaker here would produce sound, and the more we turn the volume up, the sound gets louder and louder, so it gets more and more energy, right? And then if we would watch that speaker, so now we're going to turn the volume up, and if we would watch that woofer, what's it going to do as we turn the volume up as the bass drum hits? Okay. What's that speaker going to physically do is that you can watch it and it's going to move. It's going to move in and out of that speaker. Okay. And if you had a big bass drum beat or a bass guitar or something like that, the speaker is going to push out. Okay. And in front of it, what's in front of this speaker is air. So that's the medium in which the sound is traveling away from this speaker. And so the sound, as this speaker pushes out, it generates a compressional wave of sound, just like the sonar did from the bottom of the boat. Okay. And then that compressional wave will propagate through the air or through the soft tissues and then allow us to hear that. Okay. On the other hand, the tweeter in the mid-range is doing the same thing. It generates these compressional waves, but the distance between them is much less than the low frequency sound. Okay. So the thing that you need to remember as far as ultrasound goes is if we're using a low frequency probe ultrasound probe or a transducer, which we're going to learn more about here in a second, the low frequency probes are going to be probes that are going to generate a frequency in the 2 to 5 megahertz range. Okay, a high frequency probe would be one that's going to generate sound waves in the 12 megahertz and above range. Okay, so the low frequency probes that we would use in ultrasound, they have good penetration and poor resolution. So how do you remember that? Well, here's how you remember that. Let's say you're driving down the road and you're in your car and you pull up to a stoplight or a stop sign, and some car pulls up behind you. That's two cars behind you, and it's waiting in line also. And this car is owned by some teenager, and they have a big boombox stereo, and it's cranked up really loud. Okay, and you can hear it. It goes through their car, through their windows, through the air, through your windows, and into your car. Well, what do you hear from that music? Do you hear nice, crisp, pretty music, or you just hear boom, boom, boom? Well, all you hear is boom, boom, boom that's coming out of their car, right? So that's how you remember that low frequency bass penetrates through everything, through their car, through the air, and into your car and into your skull. Okay. And so that's how you can remember that low frequency sound has good penetration, but the resolution, it doesn't sound very nice. It's not clean, crisp, tight bass. It's muffled bass, and it doesn't sound very good at all. Okay. On the other hand, you can't hear the nice trebles. You can't hear a lot of the higher frequency sound because it doesn't penetrate very far through air and through the car windows. Okay. So low frequency sound and low frequency probes have great penetration. They can penetrate really deep into the tissues. In other words, you can do a great, a 200-pound dog abdomen and it'll penetrate far into the tissues. But the trade-off that you cannot get around is that the picture quality is not going to be very good. It has poor resolution. Okay. On the other hand, is if you have a high frequency probe, the picture is going to be really pretty. It has good resolution, but it doesn't penetrate very far in the soft tissues. And that's a physical trade-off that just due to how the physics of how the sound interacts with the body that you can't get around. Okay. So it's one or the other. And so there's a compromise depending on what you want to do. And so you can tell with this is if you had a cat only practice and all you're going to be doing is imaging cat abdomens, you can get away with buying one ultrasound probe, and it can be a high frequency probe to give you a really pretty picture because the cat abdomen is only going to be about that big. Okay. On the other hand, is if you're like most veterinarians and you're going to do dogs also, and you have great big dogs that come in, you're going to need a lower frequency probe to be able to penetrate that much soft tissue, right? Okay, so let's take our speaker analogy one level further. So again, if I have this woofer at time 1, that woofer is going to move out like this, and it's creating this compressional wave of the air molecules in front of it. Okay, and over time, that compressional wave, where all of these vertical lines are close together, will propagate forward. So at time 2, that compressional wave has moved forward in the air. Okay. At time 3, it's even moved forward to here even more. Okay. As this woofer moves in and out, here it's moving out and causes compression of the air molecules in front of it. Here it moved back in towards the speaker. And that area between these compressional waves is called, where there's no compression of the waves at all, that's called an area of rarefaction. So that's an area where there's no sound produced. And on either side of it, you have a disc or volley or compressional wave of sound that's produced from this speaker as it moves in and out. Okay. Well, the ultrasound probe does the same damn thing. Okay. It's basically a speaker that's moving in and out physically, and it creates these compressional waves that you can see here diagrammed here into the soft tissues that propagate into the soft tissues of the animal. So basically through water. Okay. So if I have a probe that is sending out sounds in the frequency of 3 megahertz or 3 million cycles per second, okay, I'm going to get compressional waves that are this far apart. Okay. If I cut that frequency in half, then now I have a compressional wave that's only half of that. So I have these areas between them that has more distance where there's no sound produced. Okay. So now we have to talk about resolution. And when we talk about imaging, we talk about how crisp the picture looks. And you can even use this analogy if you have a digital camera or your iPhone and you're taking a picture. Obviously, if you take a picture of somebody, you want their face and everything else to be nice and crisp where you can really see it, and it's a nice, pretty picture. Okay. On the other hand, if everything's really blurry, that would be poor resolution, and no one likes to look at a picture that has poor resolution. Okay. When we looking at medical images, resolution is really defined by the ability to distinguish two small objects that are really close together. So I can take two little dots, if you will, and if they get some point where they're so close together, like these two blue rectangles here, at some point in time, if I started pushing them closer and closer and closer together, okay, there's going to be a point in time where I really can't tell there's two. It's going to look like one big one. Okay. On the other hand, if the space between them gets bigger and bigger, it's easy to tell there's two. So that's good resolution. Here, I'm able to resolve there's two separate distinct blue boxes. Here, I'm not able to resolve that there's two separate distinct blue boxes because they're getting closer and closer together. So obviously, resolution-wise, with any kind of medical imaging, if we have two nodules in the liver and they're really small, okay, we want to be able to tell, no matter how close they get together, that there's two separate distinct nodules. We want to see that area of resolution that looks really pretty and nice and crisp. Everything's defined, okay? We don't want everything just to kind of blend together, which would be a poor resolution picture. In ultrasound and medical imaging, there's really two types of resolution. So understand it this way. If I had my two dots right in here and on the horizontal plane, okay, if they become so close together right now, you probably wouldn't be able to tell that there's two dots. It looks like one big one, okay? That's on the horizontal. So horizontal resolution is across the plane of the animal. When they become closer and closer together, we still would like to be able to resolve that there's two dots, okay? Axial resolution is now when they're stacked on top of each other, okay? So if they're stacked on top of each other, the concept's the same, say, but if they became really close together, I might be able to tell that there's two separate dots. It might look like there's only one, okay? So if you look at this cartoon, here is an animal or a patient or a human or whatever. Here's the ultrasound probe on the top of their belly, and this is part of the liver, and I have two different dots right in here, okay? On the horizontal plane, if they are this far apart, I can tell there's two different dots or two different nodules in this ultrasound image. On the other hand, if those nodules start to become closer and closer together in space, at this point in time, they kind of blend together and they look like, instead of two nodules, they look like one big nodule. Okay, so the objects are unresolved or poor resolution. Here they're resolved. This is better resolution. We want an ultrasound machine that no matter how close these nodules get together, we still want to be able to see and define that there's two of them instead of just one. Okay, that's horizontal resolution in a horizontal plane. Okay, axial resolution is again where the same thing, same concept, there's two nodules, but now they're stacked on top of each other. So here, there's a nodule here, there's a nodule here, a little blip on the screen. There's enough distance between those nodules, I can still see there's two. On the other hand, if those nodules become closer and closer together, now they blend together and it looks like there's one. Obviously, with any kind of ultrasound machines, we want the best resolution we can get so the picture is the prettiest, whether it's in an axial dimension or horizontal dimension. Okay, the other thing that you need to realize if you're shooting ultrasounds, you're holding the transducer and you're shooting the ultrasound waves into the body, okay, is that all of these transducers, even on the bottom of the boat that we looked at a minute ago, they have a dual function, okay? 99% of the time, they're actually not sending out sound. They're waiting for sound. They're like all ears. They're waiting for sound to come back to the transducer, and then it converts that incoming sound to some type of information that's useful, okay? In our case, it's making a picture of it, okay? Only 1% of the time when you're ultrasounding a dog, only 1% of the time is that probe actually sending volleys of sound out. The rest of the time, the great majority of the time, is listening for incoming sound that's reflected off of things that it makes the picture of. Okay, sound wave, like we said, is a wave form of energy. just like light is, right? So visible light that we see. So think of it like this: if you have a flashlight and you turn the dim the lights in the room, and you push that flashlight. Let's say that this is my flashlight, and here's a wall, right? If I have the flashlight on and I put it right next to the wall, is that circle of light on the wall? It's going to be really well defined. The edges are going to be well defined, and it's going to be crisp and looks really pretty. What's going to happen is if I move that flashlight further and further and further from the wall, what's going to happen with that light that you see on the wall? Well, two things. One is the further away you get, the light's going to get bigger and bigger. It's going to spread out because the light diverges. Okay. And the further and further away I get, the light becomes less and less bright. So it dims. And then the further I move this thing out, the edges of the light will become less and less distinct. It becomes more fuzzy in appearance. We all know that by playing with flashlights, right? Well, sound has the exact same properties because it's another waveform of energy, just like light is. And so if I have a probe that's sitting right on the ultrasound on the surface of the dog's belly, and the spleen, let's say, is right underneath the skin, okay, the spleen is going to look really pretty because now that flashlight, if you will, is right next to the spleen or the wall of the when we're playing with the flashlights. Okay, so the spleen looks really pretty because it's up near where the probe is. That's called the near field, and the Germans named it the Fresnel zone. Okay, so the near field, everything in the near field looks really nice and pretty. But the further deeper and deeper you get into the soft tissues that you're trying to image, so let's say now you're trying to image an adrenal gland that's 10 centimeters deep in the tissue. Okay, that sound that's coming out of the probe then does the same thing the flashlight does. The sound dissipates, it's not as powerful, so the image quality goes to hell. Okay, and the sound waves diverge, so there's not as much sound per unit that we can see, and so the picture becomes poor quality. The edges become a little more fuzzy, and there's just not as much sound, just like there wasn't as much light when we pulled the flashlight away from the wall. So everything in the near field, near where the probe is going to be pretty. And everything, the deeper and deeper and deeper you get into the tissues, the picture starts to kind of fall apart a little bit. It's not as pretty. It's not as, the resolution isn't as good. Okay. So ideally, with the engineers, when they design ultrasound machines, they want to keep that narrowed beam diameter, even if it's in a deeper part of the tissues. And so there's ways that they can actually focus the beam back into a narrow diameter to keep it from diverging away, just like it would from a flashlight. And so you can electronically, they found ways that they can go in and make the beam form a narrow diameter so it keeps it from diverging as it goes deeper and deeper into the soft tissues. And that's called focus. And on most of these ultrasound machines, you can electronically adjust the focus of the beam to a particular depth in the body to where you can maintain good resolution even at a deeper depth. Okay. That slide I wouldn't worry about. I'm not going to worry about that. So let's go to transducers. Okay, what is a transducer? A transducer is the probe that you hold in your hand when you're doing an ultrasound. And a transducer is an electronic device. Basically, it converts one form of energy into another form of energy. Okay, so for the purposes of ultrasound, the transducer that you hold in your hand, it takes electrical energy out of the ultrasound machine from the wall socket, and it converts that electrical energy into sound energy, sends that sound energy into the body. That sound then reflects off of things, comes back to the probe, and the probe then converts that sound energy back into electrical energy, shoots it back into the ultrasound machine, which the computer then magically creates an image. Okay, so ultrasound transducers take electrical energy, convert it into sound energy, and then they're listening 99% of the time. They take that sound energy and reconvert it back into electrical energy. Okay, ultrasound transducers, all of them now are what's called electronic transducers. When they're on, you can't feel that they're on. You have no idea they're on. They don't vibrate. They don't do anything. They don't get hot. Okay, you don't know they're on until you would touch them against the skin on something and see if it makes a picture or not. All of these machines, you can freeze or pause the picture, and save it. Okay. And then you would unfreeze it or press that button again. And then that probe is active, making sound again. Okay. And then it will make another picture. Okay. The other thing to realize about ultrasound transducers is that the probe size and shape have nothing to do with the frequency. So I can have an ultrasound transducer that is the size of a pencil eraser, but it could still be a high or low frequency probe. So the size with ultrasound, the size doesn't matter at all, and it has no correlation at all with the frequency. Okay. So how do you know what frequency it is? Well, usually it'll say on the probe, or it'll say on the end of the cord where you plug the probe into the machine, it'll say its frequency. So it'll say it's a 5 megahertz probe or a 20 megahertz probe or whatever. So that's how you can tell, because by looking at it, you can't tell the frequency. Here are 3 different ultrasound probes. Here's a penny just to give you an idea of size. So here's a little sector probe here. This probe would generate kind of a pie-shaped image. But I can't tell you if this is a 20 megahertz probe or a 2 megahertz probe. Okay. This is another probe, different footprint, larger footprint where it actually touches the skin. Okay. But again, I can't tell you what frequency that probe is. So what's inside one of these probes? So here's our probe. You can see here's the cord. That's, it would be a long cord that plugs into the machine. And here's the probe housing that you can see. The probe's made out of this tough plastic. And then this gray area is this rubberized area. And that's where the sound actually, that's the window where the sound comes out of the probe in all 3 of these. So if I took a cross-sectional and look inside of one of these things, the heart of the probe is this little white line, which is blown up a lot bigger than it should be. But it's this white line, and that's called the ultrasound crystal, which we'll talk more about in a minute. On either side of that crystal, this is the actual thing. The crystal is what makes the sound waves. So that's the woofer, if you will, of this speaker. Okay. So if I'm looking at this crystal, on either side of the crystal, I have a wafer thin metal structure. Okay. So that's, imagine that it's a crystal. This is like an Oreo cookie. And the white stuff in the middle is the crystal. And the metal on either side of the Oreo cookie is the chocolate part, right? And so it has an electrode or a piece of aluminum foil on this side of the crystal, and another electrode or piece of aluminum foil on this side of the crystal. And each one of those is supplied with its own electrical energy, its own little wire coming to each one of those. Okay. Behind the crystal is I have this gray stuff in here called backing material or a backing block. And that backing material is usually made out of cork or it's made out of some type of rubber. And the purpose of the backing material is when this crystal makes sound waves, they go out in every direction. Okay, so they go out this way, behind the crystal, to the side, and also through the front where we want them to come out. So this backing material absorbs the sound that go in the wrong direction. Okay, because that sound then would just make the picture uglier. Okay, around the crystal, then I have the plastic housing, and then in the front is this matching layer up here in the front, which is that gray area you saw in the real probes a minute ago. And this is where the sound would come out. Okay, so that's kind of what's inside one of these probes. Now, what is that crystal actually made out of? The white part that's in the middle of the Oreo cookie. Okay, that crystal in all of these machines is made out of a ceramic called lead zirconate titanate. Okay, and that ceramic material has what's called piezoelectric properties. And if you remember, you might have remembered that word a little bit when we took physics, undergrad physics. Something that exhibits piezoelectric properties is, again, it's a transducer, but something that has piezoelectric properties is if I push on it, if I press on it with, and put pressure on it with my finger or anything else, it then turns that pressure energy and converts it into electric energy. Okay. And the opposite would be also true, that if I shot an electric energy into it, the crystal, instead of indenting, it would change shape in response to that electric energy. So that's something that has piezoelectric properties. And the best example of this, to make it a real world home thing, is if you come up to an intersection in the road, and typically you're coming up and, here's an intersection, it's got a stoplight, and you look at on one corner of the intersection, there's a big metal silver box, which inside of it, there's a computer, okay? And then if you look at the road, it has these things that are cut in the road. So it has this groove that somebody used a machine and cut a groove in the road. And what they did then is they buried a wire inside that groove and they covered up with this tar stuff. Okay, well, that wire has piezoelectric properties. And so when a car, the weight of a car comes up and drives on it, the weight of the car, the tires will put pressure on that wire, which generates a very small electric pulse. And that wire then feeds over to that box on the corner of the intersection and tells the computer, hey, there's a car sitting here and let's change the light so the car can go. Okay, so that wire has piezoelectric properties. The pressure or weight of the tire generates an electric pulse, which causes an action by that computer. Okay, then, you know, typically there's another one cut out a little bit further, and there may be another one cut out a little bit further down here. So now the computer says not only is there one car, now there's 2 or 3 or 6 cars or whatever that's backing up. So now we need to change the light, but it detects more and more cars. Now it says we need to keep the light on for a longer period of time to let those cars go. Okay, so that's the real world example that has piezoelectric properties. Well, our ultrasound probe is the same thing. Okay, so what happens when I put an electric pulse on that crystal right in here in example A, there is no electricity supplied. And so that crystal has a certain length and width. Okay, on the other hand, if I pulse a pulse of electricity into it, so now I've charged it, all of these crystal elements line up together. And if you notice, what's the difference between here is the crystal has now become longer and skinnier than when it doesn't have an electric charge. So if I vary that, let's say 3 million times a second, so a 3 megahertz probe, what's that crystal going to essentially do? It's going to essentially vibrate and snap back and forth between these two shapes 3 million times a second. And when it does it, it's acting like a woofer. It's moving back and forth, and it's causing these progressional waves in the soft tissues, i.e. our body, right in front of it. Okay, so again, it's acting like a woofer. As that crystal changes shape, it's causing compressional waves of sound as they enter into the body or the soft tissues in our body. Okay, so that kind of goes all back to this speaker analogy on how it generates sound waves. Okay, once the sound leaves the crystal, then it goes into our body and travels through our body, and it can interact with the soft tissues in our body or whatever it bounces off of in 3 different ways. Okay, the way that the only useful one of these is the sound that is reflected off of something. And so if we send out, we put an ultrasound probe on the top of the dog, we send the sound out, the probe's active, it goes into the dog's abdomen. As that sound would reflect off of a stone inside the urinary bladder, a portion of that sound then would reflect back towards the probe. The probe hears that sound and converts that into an image, and we can recognize there's a stone in the urinary bladder. So the reflected type of sound is the only type of sound interaction that's useful to us, okay? Because it helps us make a picture. Other portions of the sound is attenuated or absorbed by the body. Okay, so the sound that doesn't bounce off stuff, it goes through the body. And again, the deeper and deeper and deeper it would get into the body, the less and less sound there is. It gets absorbed or attenuated the deeper it goes into the body. Okay, so in reality, that sound is converted into heat, but it's so much heat and it's so little heat, it dissipates, you know, in the soft tissues, and you would never know it. Okay. There's another interaction, which is refraction of sound, which I'm not even going to get into that. Basically, it's not useful to us, so we're not going to worry about that. Okay, of the reflected sound, we need to know that if the sound wave bounces off something that's smooth, it's very predictable on which direction the sound wave will reflect in. Okay, if that's the edge of that surface is really irregular and lumpy, bumpy, it's going to, the sound wave as it comes in, it's going to reflect off in all kinds of different directions. So why do we need to know that? Well, the only reason we need to know that, let's take the kidney of a cat, for an example. If we have a 2-year-old cat that's normal, the outside part of that kidney, the capsular margin of the kidney, typically is going to be very smooth and glossy and kind of a white sheen if you would look at it grossly, okay? If we shot a sound, these incoming blue arrows is our vector of sound wave that comes in and it's going to interact with that capsule of the kidney. We can predict very much so exactly what angle, and almost all of that sound is going to come back at that specified angle and create a nice, thin, crisp white line that we're going to see on the ultrasound picture. On the other hand, if we have a cat that's 14 and has very small, he's got chronic renal disease, he's got very small, misshapen, lumpy, bumpy kidneys. Now we're going to shoot the same blue arrows of sound into it, but now we have much less predictable sound waves as they bounce off and reflect off of those irregular edges of the kidney. So we're going to have much less sound that's going to come back to generate a picture with. So the end result of that is if we have a surface that's really roughened in appearance, we're going to have much less sound that generates the picture. So the picture of that interface, so that in this particular case, the capsule of the kidney, the picture looks really ugly and kind of thick and not very well defined. And that's because we don't have as much sound generating to form a picture. Okay. Okay, and then the last thing we'll leave off with before we take a break is the Doppler effect. Now we all know what the Doppler effect is, and the Doppler effect is used medically when we're doing ultrasounds if we have color flow features on the machines, and most all of them do nowadays. Okay, the easiest way to describe the Doppler effect is an analogy. If let's say if you're sitting, okay, here's what we're going to do. We're going to back up and we're going to say, okay, you're going to go outside and you're going to you have this fetish for trains. You like trains, right? And so you're going to go to the nearest train track near your house, and you're going to take a bottle of water and a Coors Light, and you're going to set up a lawn chair next to the train track, okay? Because you like trains, and that's the way you like to do things. And so you're going to wait for the train to come by as you sit in your lawn chair. Okay, and you look down the track and finally you see the train coming your way and you get all excited. Okay, and as that train comes your way, he's let's say he's traveling 50 miles an hour. Okay, as that train comes by, what you're gonna do is you're gonna do this because you want him to blow the horn on the train as he comes by, and he sees you, so he starts blowing the horn on the train as this train zips by you at 50 miles an hour. Okay, what are you going to hear as that train comes by and he's blowing his horn? Okay, what you're going to hear is you're going to experience the Doppler effect. Okay, we've all know this, we've all done this, but you may not have put a name on it. And so that train whistle, let's say it's a high pitch and it's going, but as soon as that train gets right next to you and then goes past you, the pitch on that whistle will go from high to low immediately. Okay, so and you're going to laugh at me, but the train's coming by, its whistle's blowing, it's going choo choo. But as soon as it comes by you, it's going to go choo choo like that, right? Okay, that's the Doppler effect. And the difference in how much the pitch goes from a high pitch to a low pitch is again, that's the Doppler effect, and that's the amount of Doppler signal that train will deliver. So it's dependent on several things. Let's say now you're sitting there and another train's coming by, but this train's not going 50 miles an hour. This train's going 5 miles an hour. So it's going much slower. Okay. And he does the same thing. He's blowing his horn as he drives by you. What are you going to hear then? You probably won't hear much Doppler effect at all, because now the train's going so slow, you won't experience that Doppler effect. And it's kind of intuitive when you think about it. So what we know then is the amount of Doppler effect is totally dependent on several things. The biggest one is the velocity of what's traveling, what's moving. Okay. In this particular case, it was a train. The faster the train would go, the larger the Doppler effect would be. It would go from a high pitch to a much lower pitch. If the train goes really slow, you probably wouldn't experience much of a change in pitch of the train whistle at all. Okay. So this is the Doppler equation. You do not need to know this. Okay. But notice that this is velocity. So that's how fast the train is going. And it's also dependent on the cosine of the angle. Okay. The cosine of the angle of which the train's coming to you. Okay. But the main thing it's dependent on for medical purposes is the velocity. Now, in our bodies with ultrasound, we don't have trains and we don't have train tracks, but we do have moving particles. Okay. And so what the Doppler ultrasound looks at, instead of trains, it looks at red blood cells. So it looks at it's sound waves that are bouncing off red blood cells in our veins and in our arteries. That's what we're experiencing when we do color flow. So now we have this is you sitting here in your lawn chair. That's the probe. We're sending out a sound wave at a particular angle. And that sound wave reflects then off of red blood cells as they're traveling through that blood vessel. And if the faster the flow, just like the faster the train, the more Doppler effect is going to be generated that we can see on the probe. Okay. If we have really slow flow through that area, like a vein is going to have much slower flow, then the Doppler effect isn't going to be as large. Okay. So this is an example here. Here is a train or a red blood cell, if you will, sitting in the middle of this picture, and it's generating sound waves, and it generates them circumferentially all the way around it. And you can see these sound waves are these circumferential rings, and between them, those are volleys of sound. Between them are areas of rarefaction where there's no sound. Okay, but this particle is not moving. Okay, things change once we set that particle in motion. So once the train of the red blood cell starts to move, this is what we see. So now it's moving to the right. All of the sound waves in the direction that it's moving become compressed together. All of the sound waves away from the area that it's moving become further and further apart. Okay. Well, what if we increase the speed of it even more? If we increase the speed of it even more and do it at the speed of sound, now our particle is right on the leading edge. Okay. If I was sitting in my chair right here, as soon as that gets to me, what is that impact of that sound what are you gonna hear? You're gonna hear nothing until it gets right to you. And then when it gets to you right there, you're gonna have this concentration of sound where everything's packed on top of each other, okay? And what we ended up with that was back early on when they were doing flights and with NASA and that kind of stuff. That's when you hit the speed of sound, that's called a sonic boom. And so they didn't realize what it was back then, but as soon as that jet fighter would hit and be equal to the speed of sound, if you were sitting right below it, you would get this compression of energy that's right there, and it would cause this loud boom. And that's what those people were hearing, the sonic boom, as soon as that jet fighter would hit Mach 1 or the speed of sound. Okay. If we go back to this example, once that jet fighter gets faster than the speed of sound, we would have we'd have no sonic boom anymore, because now you wouldn't even hear it. You wouldn't hear it sound at all until it got past you. Okay, so that's kind of cool. Okay, so the Doppler shift is important. We see that with sound waves as it bounces off traveling red blood cells. We know that the faster the blood flow, the better the Doppler shift it's going to have, and it will be easier to pick up with an ultrasound probe. Okay, so if we can calculate the amount of Doppler shift because of the velocity as part of that equation, then we can rearrange the equation and we can tell how fast the blood is going in that particular vessel. So once we see the Doppler shift with the ultrasound, then the ultrasound machine, the computer, then can tell us the velocity of blood flow in that vessel. So that's kind of cool. So by ultrasounding an artery inside the animal, if you have Doppler capability with your machine, which most of them do, not only can we see there's blood flow in the vessel, but we can calculate the velocity of the flow of the vessel. Okay. Then if you remember the last thing before we get off of this boring stuff, the last thing, if you remember, is again back from physics. If there's this thing called the Bernoulli equation, okay, and if we know the velocity of something, we can also calculate the pressure inside of that vessel. So if we take 4 times the velocity squared, that will calculate and give us the blood pressure. So now, not only with Doppler, because of this train thing and that phenomenon that happens, we can calculate the velocity of blood flow in an artery. But now that we know the velocity, we can also calculate the blood pressure in the artery. So that's all kind of cool stuff. Color flow ultrasound. Let's see, we are past. Let's take our 10-minute break or so. We're going to come back and talk about color flow. Okay.